Welcome to The Explainer. Today, we're going to pull back the curtain on the tiny, powerful brains that run so much of our world. PIC microcontrollers. We're going to go on the whole journey, from a simple idea kicking around in your head, all the way to a real working electronic device. So, let's dive right in.
You ever stop and think about something like an electric toothbrush? I mean, how does it know to turn on, or switch between modes, or even time you for 2 minutes? Well, it's not magic. It's actually a tiny dedicated computer, a microcontroller, that's running just one single program to do its one job perfectly. And that, right there, is the heart and soul of embedded systems.
So you might be asking, what's the difference between one of these microcontrollers and, say, the super powerful microprocessor inside your laptop? Well, think of it like this. A microprocessor is a big general-purpose brain. It's brilliant, but it's kind of helpless on its own. It needs all this external support, RAM, storage, all that stuff. A microcontroller? It's a completely different beast. It's a self-contained system on a single chip. Everything it needs, the brain, the memory, the inputs and outputs, it's all baked right in. This makes it a specialist, perfectly designed to do one thing incredibly well, super reliably, and for way, way less money.
Okay, so we know what these tiny brains are, but how do we actually tell them what to do? Well, you're going to need the right combo of software and hardware tools to turn the code you write into real actions out there in the physical world.
First up is the software, and the best part is, the folks who make the chips give you everything you need for free. You'll be using something called the MPLAB-X IDE. That just stands for Integrated Development Environment. The easiest way to think of it is as your project's command center, your digital workbench, where you write code and keep everything organized. And then you've got the XC8 compiler. Now this is where the real magic happens. It's basically a universal translator that takes the human-friendly C code you write and turns it into the raw ones and zeros that the microcontroller can actually understand.
Now, over on the hardware side of things, a few tools are just non-negotiable. A multimeter is your best friend for doing quick checks. Is there voltage here? Is this connection good? But the real star of any electronics bench, the single most important tool you can have, is an oscilloscope. This thing lets you literally see the invisible electrical signals dancing around your circuit in real time. It turns wild guesses into hard facts. It's an absolute game changer for debugging. And of course, you need the PIC microcontroller itself, the little brain we're going to be teaching.
So how in the world do you get your code from the computer onto that tiny little chip? Well, meet the PICs. This little red box is the essential bridge. It actually plays two critical roles. First, it's a programmer, which means it physically loads your code onto the chip. And second, it's a debugger. This is amazing. It lets you peek inside the microcontroller's brain while it's running to see exactly what's going on and figure out why things aren't working.
And hooking it all up? It's actually pretty straightforward. A regular USB cable runs from your computer to the PICs. Then, a special little 6-pin cable goes from the PICs to your microcontroller. This uses a protocol called ISCP, which is just a fancy acronym for in-circuit serial programming. All that means is you can program the chip while it's still sitting in your circuit. No need to pop it out. It creates a perfect direct line from your keyboard to the hardware.
All right, so our software is installed, our hardware's on the bench, we're ready to go. Now we get to the really good stuff, writing the actual instructions that are going to bring our little device to life.
Okay, before we write a single line of actual logic, we have to talk about the golden rule. This quote says it all. If the configuration bits are not set, the microcontroller will not run. Period. These are special settings that tell the chip really basic stuff, like what to use for its heartbeat, its clock source. If you get this step wrong, nothing else you write will matter. The chip will just sit there.
Pretty much every single program you write for one of these chips is going to have the same basic structure. First, you've got your includes. You'll always have #include xc.h. Think of this as a dictionary that defines all the special names and features for your specific chip. Second, you've got those all-important configuration bits, set with that #pragma-config command. This is where you lay down the fundamental rules of the game for the chip. And finally, you have the main function. This is where the action happens. It's the starting point for your program and where all of your logic lives.
So the whole workflow inside that MPLAB-X software is a really clean, logical process. Once you've written your code, you kick things off by compiling it. That's step one, where the XC8 translator does its thing. Then you tell the software, hey, I'm using my PICs as the programmer. And finally, you hit the program button and whoosh, your code gets downloaded right onto the microcontroller. It's a simple 4-step dance.
Okay, so once you master that basic workflow, write,
compile, program, a whole universe of possibilities just explodes open. This is that magic moment when you go from just typing on a screen to actually making things happen in the real world. So let's check out a few cool examples of what you can do.
For instance, you can get super precise control over things using a trick called pulse width modulation, or PWM. Instead of a pin just being on or off, PWM is like flicking a switch on and off thousands of times a second. By changing how long it's on versus how long it's off, you can control the average power. This is how you can smoothly dim an LED from totally off to full brightness, or perfectly control the speed of a motor. You get all this analog-style control from a simple digital signal. It's so cool.
Or hey, what if you want your project to talk? You don't need to be some kind of audio expert. You can just grab a simple text-to-speech module. Your microcontroller sends it plain old text, and the module handles all the complicated stuff to create a clear spoken voice. It's a perfect example of how you can add some really complex features just by plugging in a little specialized part.
Want to take it even further? You can connect your device to the entire internet. By hooking up your PIC to a cheap little Wi-Fi module, like the super popular ESP8266, your project can suddenly send sensor readings to a website, get commands from anywhere in the world, or even shoot you an email. This is how your little standalone gadget becomes a real part of the Internet of Things. But maybe you don't need to reach across the globe. Maybe you just want some easy, convenient local control. Well, adding a common Bluetooth module like the HC05 is incredibly easy. This lets you connect your project directly to an app on your smartphone, basically turning your phone into a custom-made wireless remote for whatever awesome thing you've just built.
So you can see how fast you move past just making a little light blink. Once you have these fundamental building blocks down, you can start combining them to create really sophisticated, interactive, and connected devices. Honestly, the possibilities are only limited by what you can dream up.
So, we've walked through the core ideas, the tools you need, and the basic workflow to make it all happen. You officially have the map to take an idea from inside your head and turn it into a real device that you can hold in your hand. So, there's really only one question left. What are you going to build first?